This video is about how to do stoichiometry in combination with gas laws. So you remember in stoichiometry, there are 3 steps. First step is to change to moles. The second step is to use the mole ratio. Third step, change to units. So let's see if we can do this problem using those 3 steps. So number 9. You're looking for the mass of hydrochloric acid that can be reacted with calcium carbonate to make 50 milliliters of carbon dioxide. So we need to change our 50 milliliters into moles. When in previous problems, we would have just used the 22.4. And to change this to liters, and 1 mole is 22.4 liters. However, in this set of problems, we can't do that because it's not at standard conditions. The 22.4 only applies at standard. So we're going to need to find, we could do one of 2 things. We could change this from these laboratory conditions to what it would be at standard and then use the 22.4. Or we could just do it the easier way, which is to use PV equals nRT. So since we're doing this whole course now online, I'm going to go the easy route so that it's not quite as stressful. So the pressure is 1.15 atmospheres. Remember, we are trying to do step 1, change to moles. Since this is a gas, we can use the ideal gas law and solve for N. The volume we know is 0.0500 liters. So just reminding you, I'm not going to, in the future in this little video, I'm just going to do this in my head, but if I have 50 milliliters and I wanted to change to liters, I'd put milliliters here, liters there. 1 is 1,000. Remember, a thing is 1,000 millithings. So 50 divided by 1,000 is 0.05. I put the 00 on because zeros at the end of the number are significant if there's a decimal point. Okay, we don't know N. Since pressures in atmospheres, our R value needs to be the R value that had atmospheres in it. So that's 0.0821 liter atmospheres over mole Kelvin. And then the temperature would be 297 K. 297 K. 297 because it's 24 plus 273. So then we need to get a calculator and actually do the math. So I have a calculator here. Put it up here. I'm trying to get this out of the... There we go. Kind of make room for everything. So our calculators, to do that, we're going to multiply the 1.15 by the 0.05, then divide by the numbers that are with the variable. Be sure that you understand your algebra, that you need to get this by itself, so you're going to divide by the things that are with it. All right, so over here, we have 1.15 multiplied by 0.0500. We're going to divide that number by 0.0821 and then divide again by 297. So we end up with 0.00236 moles. Sometimes I double check my math, so 1.15 times 0.0500 divided by 0.0821, then divide again by 297. Looks good. So that's the moles of CO2. Now if you look at your equation, we know that there's a 2-to-1 ratio between the CO2 and the HCl. So we've done step 1, change to moles, 0.00236 moles of CO2. We're going to put moles of CO2 on the bottom. This is the mole ratio step. Moles of HCl on the top. There are 2. There's 1. And once again, I got the 2 and the 1 from the equation. 2, 1. Then we need to change to grams, change our desired unit, which is grams. So we'd have moles of HCl on the bottom, grams of HCl on the top, 1 mole, 36.5 grams. And I got that by adding H, which is 1, plus chlorine, which is 35.5. So I'll go ahead and take this number. Technically, you should round at the end to the appropriate number of significant figures. So I'm going to multiply that by 2, multiply that by 36.5. There's nothing on the bottom over here to divide by. So the answer is 0.172 grams of HCl. Remember that these numbers do not limit your sig figs because they are definitions. They're exact numbers. It's exactly a 2-to-1 ratio. That's the end of question 1. Now let's take a look at question 2, or question 10 on this sheet. So question 10 doesn't give us an equation, but that's no problem because we are competent. So we're going to take our NH3, and it's going to react with oxygen. It's going to make nitrogen and water. The equation is not correctly balanced yet, so we have to do that. We have 2 ends, we have 1 end, so we put a 2 there, which 2 times 3 makes 6 hydrogen, so we put a 3 over here. And that doesn't seem to balance the equation properly because I've got 3 O's and 2 O's. So it looks like I'm going to have to make this now become not a 3, but rather a 6. And then if I make that a 6, 6 times 2 is 12, so I'd have to have a 4 over here. And if 4 times 1 is 4, so I'd have a 2 here. And then I've got 6 oxygen, so I'd have to put a 3 over here because 3 times 2 makes 6. So that's the correct balanced equation. Just double check. 4 ends. 2 times 2 is 4 ends. 4 times 3 is 12 H's. 6 times 2 is 12 H's. 3 times 2 is 6 O's. 6 times 1 is 6 O's. All right, we have 5 kilograms of ammonia and 8 kilograms of oxygen. So 5 kilograms is 5,000 grams. And 8 kilograms is 8,000 grams. You may be recognizing that this is a limiting reactant problem. But there is some good news in that we don't have to worry about the ideal gas law because we're at STP. So if we're at STP, then that means that 1 mole equals 22.4 liters when we're talking about gases. All right, so I'm going to remind you how to do this. We change both of these to moles. So you take 5,000 grams of NH3 times 1 mole over 17 grams. And we have 8,000 grams of oxygen times 1 mole over 32 grams. So we'll do the math. We've got 5,000 divided by 17. 294 moles. I'll just leave it as 3 sig figs. 294 moles. And that's moles of NH3, sorry. And 8,000 divided by 32. 250 moles. Okay, so next thing we need to do is figure out which one of these runs out first. So I'll pick one to compare it to the other. I'll just start with the NH3 since it's on top. If I'm going to use up all of the NH3, all 294 moles, I'm going to do a ratio with oxygen. I have moles of NH3 on the bottom and moles of oxygen on the top, and that's a 3-to-4 ratio. So 294 times 3, and then divide by 4, 220.5. So I need 220.5 moles of oxygen to make all of the NH3 disappear. And if you look back here, I've actually got more than that. I got 250. So I got extra oxygen. So that means that the NH3 is limiting. So since that's limiting, we take that one to solve the rest of the question. We want to know what volume of nitrogen would be produced. So we're looking for that. Okay, so this is what we're looking for right here. So let's take our limiting reactant, 294 moles of NH3. We know we put moles of NH3 on the bottom. Remember, this is the mole ratio step. We use the mole ratio to find what's limiting. Now we take the moles of the limiting one and use the mole ratio between what we're looking for and what we have. So we put moles of N2 on the top, and that's a 2-to-4 ratio. And it wants to know what volume, so we put moles of N2 on the bottom, liters of N2 on the top, 1 mole, 22.4 liters. Again, why can we use the 22.4? Because we're at STP, and that's where that applies. So we do our math. We've got 294 multiply by 2, multiply by 22.4 equals, then divide by 4 and divide by 1, or just divide by 4. So 3,293.8 liters. If I wanted to round that into appropriate significant figures, which would be, in the problem we had 3 sig figs, so we'd end up with 329, and since that's a 3 followed by, it's a 3, I just round off the nearest tens place. Since the 9 is followed by a 3, you just leave it alone. So it's 329, put a 0 in there to hold the place, liters, 3,290. So that's number 10. Number 11. Okay, we've got the 16 grams of magnesium. No, not 16, 65.10 grams of magnesium. Well, it's reacting with oxygen too. Better write the equation. So Mg plus oxygen. That gives us magnesium oxide. This is that one that we did this in our lab, burning the magnesium ribbon, and it was a real bright light. You remember it was a white powder, it was the magnesium oxide. Then we balanced the equation just like this, and we did all this in the lab. So we have 65.1 grams of magnesium, and we're wondering how many liters of oxygen we're going to need to react with it. So how many liters of oxygen did we actually use if we burn 65.1 grams of magnesium? Well, what's the first step? Oh, it's change to moles. So let's change grams of magnesium to moles. 65.1 grams of magnesium. If you look at a periodic table, you'll find that magnesium has a mass of 24.3 grams. Put our words in first. 1 mole, 24.3 grams. Then we put moles of magnesium on the bottom. This is the mole ratio step. Moles of oxygen on the top. And 1 is 2. All right. There is an option. I'm going to give you 2 options here you could do. You could either stop it right here and have moles of oxygen, which is what we're going to do, or you could do this. You could say there's 22.4 liters per mole, and that would equal the number of liters at STP. Then you would need to change from STP into these conditions. So you'd have a V1, V2 kind of problem. But I'm going to go ahead and do it in moles. I think it's a little simpler. So we do the math. 65.1 divided by 24.3, and then divide that by 2, and that's how many moles of oxygen we would have. The temperature here is has got 3 sig figs in it, so I'm just going to leave this at 3 sig figs. When we're all done, we will anyway. So 1.3395, I'll call it right now, but we're going to round off to 3 sig figs later. So now we can do PV equals nRT, but this time we're going to solve for, what were we looking for? Volume in liters. So we'll solve for volume. So we know we've got 1.3395 moles of oxygen. We know that the pressure is 735 millimeters of mercury. The volume, we don't know. Let's put a V in. Since this is in millimeters of mercury, the R value that we would use is 62.4 millimeters of mercury, or sometimes called liter torr per mole Kelvin. Now remember, you can always solve for R if you need to by using PV equals nRT and assume you have 1 mole. So if I said I have 1 mole of gas, the temperature was 273, we're looking for R. 1 mole of gas at standard pressure would be 760 in millimeters of mercury. And the volume of 1 mole of gas is 22.4 liters if you're at standard temperature and pressure. So if you solve for R, you'll get 62.4. Right, and then the temperature in this problem is 25 degrees C, so that would be 298 K. Okay, so we have this number equals these two things multiplied together equals these three things multiplied together. So really, what am I going to do? I need to divide both sides by the number that is with the variables. I need to get this variable by itself, so I'm going to have this number times this number times this number and divide by that. So let's do it. So I already have the number moles. Is this 1.339? What all those numbers there that are not right? Whoops, didn't hit a wrong button. So we'll just write down what I wrote down here. So 1.3395. Going to multiply by 62.4. Going to multiply by 298. And I'm going to divide by 735. And I get 33.88. I'm going to round off to three significant figures. So V is equal to 33.9 liters. So basically, we're just looking at doing the same three steps we did in stoichiometry. You change the moles, you do the mole ratio, and you change to your desired unit. In this case, after we had the moles, this is moles of O2. After we had moles, we just used PV equals nRT to find volume. All right, so hopefully we're starting to tie everything together that we've been doing since spring break and right before, where we know about stoichiometry and gas laws. Now, try some of the practice problems that I posted after this video.